Welcome to the presentation on fault detection and circuit breaker patterns. Today we will dive into these key concepts and how they help ensure robustness in distributed systems. In this session we will explore three main topics: fault detection in distributed systems, the circuit breaker pattern for fault tolerance, and how we can combine these patterns to enhance system resilience. Fault tolerance refers to the process of identifying when a service or component fails or experiences degraded performance. It's a crucial part of maintaining a reliable system. By detecting faults early, we can take actions before the issue affects the end user experience. There are several techniques for detecting faults in a distributed system. Health checks are used to monitor the system's liveliness, readiness, and startup status. Heartbeat mechanisms send periodic signals to indicate service health. Timeouts and retries ensure that requests don't stall infinitely. Monitoring and logging tools like Prometheus and Grafana help track system performance, while dependency analysis can identify potential issues based on inter-service dependencies. Effective fault tolerance helps prevent cascading failures where one service failure leads to a domino effect across the system. It also improves overall system reliability by avoiding early warnings for potential issues. Moreover, continuous monitoring tracks performance trends, allowing for proactive maintenance and scaling. The circuit breaker pattern is a fault tolerance mechanism that helps stop requests from being made to a failing service. Much like an electrical circuit breaker prevents overloads, this pattern isolates failing services to avoid overloading them and causing further disruptions. Circuit breakers function through three stages: closed, open, and half open. In the closed state, the service operates normally. When a failure is detected, the circuit breaker switches to the open state, preventing any further requests. After a set time, it moves to the half-open state where limited requests are allowed to test if the service has recovered. If successful, the circuit breaker closes again, otherwise it remains open. The circuit breaker pattern provides several key benefits. It prevents cascading failures by isolating issues before they spread, improving the resilience of the overall system. It also protects system resources by stopping unnecessary requests to failing services, allowing time for recovery. Several tools help implement the circuit breaker pattern. Histric is a popular Java-based library, while Resilience 4J is a lightweight alternative that supports additional resilience patterns. Istio, a service mesh, provides circuit breaker functionality in microservice environments, making it easier to manage fault tolerance at scale. Fault detection and circuit breakers work together to enhance system resilience. Fault detection identifies failing services, while the circuit breaker patterns prevents overloading those services, ensuring that the system remains stable. For example, in a payment gateway scenario, health checks would trigger the circuit breaker to isolate the failure and maintain service availability. To effectively implement fault tolerance, use granular fault detection methods such as service level health checks. Adaptive timeouts ensure requests don't hang too long, and exponential backoff reduces retry rates to avoid overwhelming services. Fallback strategies allow the system to provide degraded functionality when a service fails, and automated recovery ensures minimal human intervention in transitioning states. In summary, fault detection helps us identify issues early in the system. The circuit breaker pattern prevents cascading failures by isolating faulty services. When combined, these two patterns enhance system robustness and ensure reliability even during failure scenarios. That concludes the presentation. I hope you have a better understanding of fault detection and circuit breaker patterns. I now welcome any questions you may have.